You know that weird feeling when you hear a certain sound and suddenly a glass on a shelf starts to hum and vibrate all on its own? Or maybe you've seen footage of a bridge swaying in the wind and thought, how is that even possible? Well, today, we're going to pull back the curtain on that invisible force. We're talking about mechanical resonance, the hidden rhythm that can, quite literally, move mountains, or at least bring down some pretty big structures.
So what is this force? It's not magic, I promise you, but it is one of the most powerful principles in all of physics. It's a phenomenon that engineers spend their entire careers trying to master, because if they get it wrong, the consequences can be absolutely catastrophic.
The answer to that question is resonance. And at its core, it's all about timing. It's what happens when two different rhythms line up perfectly. You've got the rhythm of some outside force, and then you have the natural, built-in rhythm of an object. When those two match up, the energy doesn't just add up. Oh no, it multiplies, it amplifies, and that can lead to some seriously powerful and sometimes very destructive movement.
Okay, so to really get our heads around resonance, we first need to understand what makes up any vibration. And I think the easiest way to do this is to think of it like a story with three main characters. Each one has a really specific job in how a system manages its energy.
And here they are, our three stars: the mass, the spring, and the damper. The mass is all about the energy of motion. The spring stores up potential energy, kind of like a stretched rubber band. And the damper, well, its job is to get rid of that energy. The amazing thing is, any system that vibrates, and I mean anything, from a skyscraper to a tiny guitar string, is made up of these three elements. So let's meet them one by one.
First up, we've got the mass. This is the actual physical thing in the system that's moving, the part that has weight and inertia. Its whole job is to store kinetic energy, which is just a fancy way of saying the energy of motion. The perfect example? A kid on a swing. The child and the seat together, that's our mass, building up speed and energy as they whoosh back and forth.
Next in our lineup is the spring. Now, don't get hung up on the name. This doesn't have to be a literal metal coil. It can be anything with elasticity or springiness, like the flexible deck of a bridge or the chains of that swing we were just talking about. The spring's job is to store potential energy. It's always trying to pull the mass back to its resting point, right in the middle.
And finally, we get to meet our third character, the damper. Now, this guy is the unsung hero of our story. The damper is anything that resists motion. We're talking about forces like friction and air resistance. Its whole purpose is to dissipate energy, to get rid of it, usually by turning it into a little bit of heat. The damper is the reason that swing eventually slows down and stops. Without it, things could just keep on shaking forever.
All right, now that we've met our three characters, the mass, the spring, and the damper, we can start to uncover one of the coolest concepts in all of physics. See, every single system, whether it's a tiny violin string or a massive skyscraper, has its own unique secret heartbeat. And that secret heartbeat has a name. It's called natural frequency. It is the one specific speed, the one rhythm at which an object just wants to vibrate. If you give something a single push or a quick tap and then just leave it alone, the back and forth rhythm you see is its natural frequency.
And you can totally get an intuitive feel for this. Think about it. A system that's really stiff and light, like if you flick a short plastic ruler on the edge of a desk, it vibrates super fast, right? That's a high natural frequency. But now picture a system that's really flexible and heavy, like a huge suspension bridge cable. It sways back and forth very, very slowly. That's a low natural frequency.
And believe it or not, this entire idea boils down to a really elegant and simple little formula. The natural frequency is basically just a dance between our first two characters, the stiffness of the spring, which we call K, and the size of the mass, M. The stiffer the spring, the faster it wants to vibrate, and the heavier the mass, the slower it wants to vibrate. That's it. This little equation is like a secret code that governs so much of the physical world.
So, we've got a system, and it has its own personal rhythm, its own unique heartbeat. But what happens when an outside force comes along and starts pushing it? This, my friends, is where the magic and the danger really begins. This is the resonance effect.
This quote just nails it. Let's go back to that swing one more time. If you just give it random pushes, not really timing it, not much happens. But if you time your pushes perfectly, if you give that little nudge at the exact moment the swing reaches its peak and starts to come back, it goes higher and higher with almost no effort. You are in resonance with that swing.
And this chart shows you exactly what's happening there. Over on the left, when your pushing frequency is way off from the swing's natural frequency, the size of the swing's movement, we call that the amplitude, is pretty small. As your timing gets closer and closer, the swing gets bigger. But right at that sweet spot, when the frequencies match perfectly, bam! At resonance, the amplitude just spikes, becoming huge, maybe even dangerously so.
And get this is the truly wild part. In a perfect, theoretical system with absolutely zero friction, no damper at all, the math says that at resonance, the vibration wouldn't just get large, it would grow to infinity. The system would literally shake itself to pieces.
Okay, so this is obviously more than just a cool physics puzzle. This has massive real-world consequences. So how do engineers design things that can handle these incredible forces? How do we tame the shake? Honestly, this is one of the most critical challenges in all of engineering. Because if resonance is just left to do its own thing, the dangers are very, very real. We're talking about catastrophic structural failure, buildings, bridges, you name it. In machines, it causes parts like gears and bearings to wear out incredibly fast. And even in the best-case scenario, it creates a ton of unwanted and seriously loud noise.
So who saves the day? Who keeps our world from shaking apart? It's our hero from the beginning, the damper. By adding damping to a system, engineers give all that runaway energy a way to escape, usually by turning it into harmless heat. Damping is what keeps that spike on the chart from going to infinity. It controls the vibration and keeps our system safe and sound.
So the next time you're riding in a car and feel the shock absorbers smoothing out the bumps, or you look up at a skyscraper and realize it's designed to sway just a little bit in the wind, I want you to remember these hidden rhythms we talked about. You're seeing brilliant engineering designed specifically to control resonance. So now that you're in on the secret, take a look around. What else can you spot that's built to tame